College algebra students, welcome to my presentation of section 5.5, where we're going to be talking about zeros of polynomials. So we're going to be putting together synthetic division, the factor and remainder theorem, in order to find zeros of polynomials. So to begin with, a couple of things I want to go over. A real zero of a polynomial is a value of x which makes the function value of the polynomial function equal to 0. So you're finding a special number here. When you plug x in the polynomial, you get 0. We're going to look at real zeros first, and if you have a real number 0, then that will be an x-intercept of the polynomial function. When we look at complex zeros a little later in this section, that will not be represented by an x-intercept. Okay, we learned the factor theorem. The factor theorem just basically says if you had a factor something like x minus 3, and if you synthetically divided a polynomial by 3 and you got a remainder of 0, then that would show that that is a factor of that polynomial. So if you know one factor of the polynomial, then you can generally use the factor and the synthetic division to find other zeros. A key thing that you want to know is that the degree of the polynomial will always give you the maximum number of zeros of a polynomial. So if you had a fourth degree polynomial, you're going to have 4 zeros. You can't have more than 4 zeros. If you had a 10th degree polynomial, you're going to have 10 zeros. Now, some of those zeros can repeat because they'll have a higher multiplicity, but that gives you the maximum number of zeros that you can possibly have on a polynomial function, which to me is very fascinating. All right, so let's go down this example 1. And what I'm given here is we've got a polynomial function, and we have a factor. I'm telling you that this x plus 2 is a factor. So we're going to use that factor to find the remaining zeros of the polynomial. So to begin with, since this is a factor, if you set that factor equal to 0 and solve that real simple equation, you're going to get your first 0. Okay, so the given 0 is -2. Okay. Now, what we're going to go ahead and do is we're going to perform synthetic division. So you want to go ahead and set up your coefficients. We don't have any missing terms, so we're going to have a 1, a -1, a -4, and a 4. Okay, if there's missing terms, we learned that you want to put a 0 in there. It's really important. Okay, now what's going to happen on this is because we know it's a factor, we're going to know that that remainder is 0 already. But let's go ahead and do the synthetic division because the results of the synthetic division will allow us to find the other 2 zeros. Okay, so we're going to bring this down like we do. -2 times 1 is -2. Add the column. When you add that, you'll get -3. Multiply. -2 times -3 is +6. Add the column, -4 plus 6 is 2. Multiply -2 times 2, you get -4. So I told you so. All right, you know that was going to happen because I told you that x plus 2 is a factor. Okay, now what you're going to do here now is these coefficients down here are giving you another factor. So remember, if we synthetically divide x to the third by x plus 2, I mean, it's basically you're just going down 1 power when you do that division. So that means that these coefficients, that will give you a 1x squared minus 3x plus 2. Okay, so that's going to be something that we can set to 0, we can factor, and then we can find the remaining zeros of the polynomial. Okay, so what I'm going to do is I'm going to set that equal to 0. And this is a quadratic equation, so you could either try to solve it by factoring, or you could go the quadratic formula. So the nice thing is this one will factor. Your first term is the x squared, so that will be x times x. Your last term is 2, so the numbers that multiply to give 2 are 1 times 2. And then we need to figure out, well, how do we make these signs work so that we end up with a middle term of negative 3x? Okay, so I'm going to FOIL together the inner term, 1 times x gets 1x. The outer term, x times 2 gives 2x. And you're trying to make 1 and 2 add up to negative 3, which is easy to do. They both got to be negative in order for that to happen. Okay, so we have our factoring, and now from here you can figure out what those zeros are pretty easily in your head. You're just taking x minus 1, setting that to 0. You're trying to figure out what makes that become 0. And again, you don't have to really show this work because it is easy to do this in your head. So your second 0 would be 1, and over here you add 2 to both sides to solve that equation. You're going to get x equals 2. Okay, so what we get then is these are the 3 zeros. Okay, now to begin with, what I wanted to explain this problem also is the degree of this polynomial is the highest power, so that's 3. So that means the maximum number of real zeros is 3. So we got 3 distinct zeros to get that problem completed then. So one of the things that I would like you to know how to do is your graphing calculator can help you understand what it is you're doing visually, and it can also check your answer. So if you'll get your calculator out, we'll go ahead and graph this polynomial function. So we're going to put in x to the third, and then we'll have minus x to the second, and then I'll have minus 4x. What did I just do? Okay, plus minus 4x, forgot to put the x in. Okay, then plus 4. And we'll just graph this in a standard window. Okay, and this should give us a polynomial function. So it's got the kind of endpoint behavior we would expect. And what I want you to notice on this then is that it's since we got 3 real zeros, these are matching up perfectly with what we got. We have a given 0 at negative 2. So right there you can see we have an x-intercept of negative 2. We have another 0 at 1. That would be that one right there. And we have another 0 at 2. Okay, so when you do this on your graphing calculator, you can trace these things if you want. If I go trace, type in the first 0, negative 2. What that's showing you is when you plug negative 2 into the function, you get 0. So that's why we call that a 0. If I trace at the other one, 1, the same thing happens. Okay, that's an x-intercept. And then finally, if we trace it 2, same thing happens. So it's verifiable what you would get then. Okay, so one thing that you might want to do on your notes that I would like you to do is just, make a really, really rough sketch of this graph, just so that you have a record of what of all these zeros mean. So we have 2, we have x equals 1, and then we have x equals negative 2 as our zeros. All right, so this is the typical kind of problem that you're going to be doing. If you're given a polynomial function and you know a factor, or if you know one 0, then you're going to have the ability to find the other zeros. This is, mostly going to be talking about a third degree polynomial. Okay, and that's mainly what you're going to be looking at is just third degree polynomials on this assignment. Okay, so let's go to the next page then. And same thing's happening. I'm giving you a polynomial function. I'm giving you that x minus 5/3 is a factor. And don't dare panic because that's a fraction. The fraction arithmetic is going to work its way out of the problem beautifully. So first of all, we have a degree of 3. That means that the maximum number of zeros that we're going to have is 3. All right, we've already got 1. So when we get this first 0, you can do this in your head. You don't have to write this step necessarily unless you want to. But I think students a lot of times forget why you can do this in your head. So what you get is x equals 5/3. Okay, so if you plug in 5/3, 5/3 minus 5/3 is 0. So that would be your first 0 right there. Okay, so what we're going to do is we're going to synthetically divide. So you want to set up your coefficients. There's no missing terms, so we have a 3, we have a 16 for the x squared term, a -5 for the x term, and finally a -50 for that term. Okay, so since our first 0 is 5/3, we're going to put that first 0 out like that. And like I said, the fractions will probably work their way out of the problem pretty quickly. So when you synthetically divide, you always start by bringing down that first number like that. Okay, so fraction arithmetic does not need to bother you. When you multiply 5/3 times 3 over 1, you can put the 3 over 1. Well, the 3's divide out. So you're going to be left with 5 right there. Okay, so just by doing that one step, it makes that, fairly simple. Okay, so now we're going to add the columns. So 16 plus 5 is 21. And again, we're going to do 21 times 5/3. Okay, like this. So again, we can go through and reduce. You're best to learn to reduce fractions before you multiply them. So 21 divided by 3 is 7. Then if I go straight across, I'm going to get 7 times 5, or I'm just going to get 35. Okay, like that. Okay, now add the column. 35 added to -5 is 30. Then we're going to have to do some more fraction arithmetic. So we're going to do 5/3 times 30 over 1, which is no big deal. You can reduce 30 divided by 3. 30 divided by 3 is 10, and then 5 times 10 is going to give you positive 50. Okay, so it did work its way out, and notice we got a remainder of 0, so that proves that that was a factor, and we have our first 0. I don't know why I put 0 in that blank there. The first 0 is 5/3. Sorry about that. All right, so now what we're going to do is you need to understand that these numbers right here give you a quadratic equation. The power goes down. We divided 3x to the third by an x term, so it went down to the second. So that 3 is going to be 3x to the second. The 21 is going to be plus 21x. And then the 30 is going to be plus 30 equals 0 like that. So we have a quadratic equation. When you solve a quadratic equation, your first idea ought to be, can I factor? If I can't factor, you got to go to the quadratic formula. So let's see what we're getting ourselves into. So one thing you want to look at is you have a 3, 21, and 30. All of those numbers divide by 3. So you can take a common factor of 3 out, and you should do this. So if I take a 3 out, that will leave me with x squared plus 7x plus 10 is equal to 0. Okay, every time you factor something, you need to check your answer. Okay, because if your factoring's wrong, you're kind of wasting your time. So notice, 3 times x squared is 3x squared. 3 times 7x is 21x. 3 times 10 is 30. Okay, then this will factor one more time. So this will factor like this. Okay, so just disregard that 3. Don't even pay attention to it. The first term is x squared, so that's going to be x and x. The last term is going to be 10, so 2 times 5 is 10. And then you're going to make the 2 and the 5 add up to 7, so that's 2 plus signs like that. All right, then to finish up the problem, again, the 3 doesn't have any bearing on the problem. If you want to do this, you can. You can always divide both sides of any equation by a non-zero number. So if I divide by 3, then I get this. Now we can solve this in our head. That's x plus 2 equals 0, which will give x equals -2 as your second 0. And then we have x plus 5 equals 0. Subtract 5 from both sides, you'll get your third 0 is x equals -5. Okay, and we can check this graphically. I think I want to encourage that you all be really sharp about doing that so we can tell we're correct on this. So if you'll get your calculator out, let's just put this thing in and see what it looks like and see if we can use this calculator to tell that we have our 3 correct zeros. So I'm going to put the original in, which is 3x to the third, and then plus 16x squared, and minus 5x, and minus 50. Okay, and let's graph that in standard window. Okay, and let's just look at the zeros. Okay, let's start at 5/3. So what you can do is go trace 5 divided by 3, and out comes a 0. So that's correct. Let's trace the -2. Trace -2. That's also 0. That's an x-intercept. And finally, trace -5. Not that. -5. Okay, and that's another 0. So it's all right. Okay, these are the 3 x-intercepts. And remember, these are real numbers. And if they're real numbers, you're going to get real zeros that are real intercepts. Okay, so that'll verify that for us. We'll do one more problem, then I'll let you try a few problems here. Okay, I just changed the window on this. This is just something I want to show you. You can always adjust the window. I just raised the y. I made the y minimum go to -50, y max go to 50. Just looks better, okay? And again, what I'm going to have you all do on your notes is just find a little place to sketch a graph like this and then put your intercepts. It doesn't have to be perfect or anything. I'm just going to put it up in this little spot right here, and then just find a little place to sketch this graph. And you also might want to just show that, that was a 0 of 5/3. This was the -5. And then the other 0 was -2. Okay, so that's how you verify it. Okay, let's go down to this third example and take a look at this one. Again, you're given a factor on this. So when we start this again is a third-degree polynomial. So that means the maximum number of real zeros is going to be 3. We already have our first one. And remember, if x minus 2 equals 0, that first factor, then that means x has to be 2 because 2 minus 2 is 0. So what we're going to do is take that first 0, 2, and we're going to synthetically divide that into this polynomial. The coefficients are 1, -4, 3, and 2. And the thing that we're going to know on this is, you're going to know that the remainder is 0. Okay, we should know that because I gave that to you. And now we just need to go through and do the synthetic division so we can get the quadratic equation that will give us the remaining zeros. So if I bring down the 1 times 2 is 2, add the column, that's -2, multiply, that's -4, add the column, that's -1, 2 times -1 is -2, so I told you so. That is your equation. Now, what this is going to be is these coefficients are going to be x squared x, and that last number is a constant term. So you're going to have the quadratic equation, x squared minus 2x minus 1 is equal to 0. Okay, so let's see. You're going to run into some issues on this. You might try to factor this, and it may look like it factors. And really all you can do is go x and x, and then 1 and 1. But the problem is this middle term and that outer term, the only way to make 1x and 1x add up to -2 is to have 2 negatives. But that is wrong, and the reason is because the last term, -1 times -1, is supposed to be -1, and it isn't. So this is going to be an example of one that does not factor, okay? You're going to run into that sometimes, so there is no factoring that you can do in this particular problem. So be careful about that. All right, so what we're going to do, I'm going to go down to the bottom of the page and we're going to put in the quadratic formula. I'll go ahead and write down the quadratic formula is -b plus or minus the square root of b squared minus 4ac all over 2a. Then we'll go ahead and put everything in. So our equation again is x squared minus 2x minus 1. That's the equation we're trying to solve. So a is 1, b is -2, and c is -1. So when I plug this in, it'll go like this. We'll have -b plus or minus square root of b squared. B is -2. Let me move this over just a little bit here so I can take up a little bit more room. So I've got -b, so that's -2, plus or minus the square root of b squared minus 4ac all over 2a. Okay, so we've learned how to work with the quadratic formula before. Now I'll just do the details of the arithmetic. This is going to give 2 plus or minus, and then this will be negative 2 squared is 4. And then this part, you would have a negative 4 times a negative 1, which would make that go to positive 4. Then you have that over 2 like that. Okay, and then what we'll have is we'll have 2 plus or minus the square root of 8 over 2. Now watch this carefully, because this is a part right here that students a lot of times, forget how to do. So if you've got this square root of 8, you can break the square root of 8 into 4 times 2. And the square root of 4 is 2, so you can write the square root of 8 as 2 root 2. So you want to go ahead and write this as 2 plus or minus 2 root 2 over 2. Okay, then from here, I'm going to just sneak down to this next page here. So you're going to have 2 over 2 plus or minus 2 root 2 over 2. So that will give you 1 plus or minus the square root of 2. That would be your other two zeros. Okay, so you need to, when you do the quadratic formula, you do need to simplify things. So our other two zeros, we're going to write one of them as 1 minus the square root of 2. The other one is going to be 1 plus the square root of 2. So there are going to be times when you get zeros that come from the quadratic formula, and you're going to leave this in this form, not decimals. These are real numbers, and the exact answer is to just write it as 1 plus or minus square root of 2. All right, so what I'm going to do now is let's go ahead and let's see what happens on this problem when we check it with our calculator. So I'm going to put in the original problem, which is x to the third minus 4x squared plus 3x and then plus 2. Okay, there's my graph right there, and this thing does have 3 zeros. I'm going to take this window, I'm going to take this back to a standard window, so I'm going to go zoom 6. That way I get a little bit better view on this. It's a little hard to tell right there that that's 2 zeros, so I'm going to adjust this window on the x's. So let's just do for x, let's do negative 4 to 4 like that. And then this would be my standard, that would be my window that I'm using. And then here's my graph. And it's still kind of hard to tell that there's 2 zeros there, but there are. So let's trace them out like we've been doing. We trace the 2. Okay, that's clearly that 0. Now you can also trace these out. You can go trace 1, subtract, square root of 2, and that's a 0. So that's right, that's that one. The other one would be 1 plus the square root of 2, and that would be this 0. Okay, so yeah, everything is checkable and verifiable on your graphing calculator. So you probably want to just sketch a graph on here, and then it would be a good idea to label these. That one is the 2. This one is the 1 plus square root of 2. And then this one right here is the 1 minus square root of 2, like that. Okay, all right. So those are 3 examples that are very similar. Take the given factor, divide, use the resulting quadratic equation to find the other 2 zeros. Okay, so I'm going to have you go to the next page. You can always pause the video if you need to write any notes or you need to process what I'm doing. Okay, because sometimes you do need to just process what I went through. Okay, so 2 problems are anxiously awaiting for you on the next page. So if you'll pause your video, and please do this, don't just resume it and just copy down the answers, because you need to try these problems and see if you can put together what I'm trying to teach you. Okay, good luck. Okay, so here are the answers that I hope you got for the first one to begin with. So it's a 3rd degree polynomial. That means you have a maximum number of 3 real zeros, and you will get 3 zeros. So the first factor is x plus 3. And remember on this, if you solve this equation, which you can do in your head, you're going to get x equals negative 3, and that's your first zero. So that's what you synthetically divide into. And you know you're going to get a 0 by the remainder and factor theorem there. So you look at my synthetic division, you should have got these numbers right here. If you didn't, go over the arithmetic. And what you're left with is 2x squared minus 5x, and then your constant at 2. So this thing did factor. Some of you may have just went straight to the quadratic formula, which is okay. You'll get the same answer that I got. So this one does factor. If you look at what I did, the first term is 2x times x to get 2x squared. The last term is 1 times 2 to get 2. And then again, this visual is very helpful to help you determine what the signs of the inner and outer term are. So that would be a negative 1x and a negative 4x required to give you negative 5x. So if you factored it, that's what you would have got. Then you can either get these two equations and solve them in your head, or you can work them out. So x minus 2 is 0. You could add 2 to both sides, get x equals 2. Over here, 2x minus 1 is equal to 0. Add 1 to both sides, divide by 2. Then you would have your other two zeros. So your answers to your zeros are negative 3 is the one you were given, 1/2 and 2 are the other two like that. As far as my graph goes, I used this window just so you can see it a little better. It's usually a good idea on polynomial functions to expand on the y values a little bit so you can see it better. But you'll see on there if you trace these out, 2 is an x-intercept. It touches the x-axis, crosses it actually. 1/2 is this 0 right here. And then negative 3 is that 0 right there. Okay, so I did want you to just make a little sketch of the graph just so that you're really confident and understand what the meaning geometrically of what we're doing is. Okay, pause the video right now if you need to write anything down, need to look at what you did, identify mistakes. Okay, otherwise I'm moving on to number 2, and you can see if you got the right answers on number 2. Number 2, you had to do the quadratic formula on. So to begin with, I gave you a factor of x minus 2/3. So your first 0 is 2/3 because 2/3 minus 2/3 is 0. And then my synthetic division, you had to do some fraction arithmetic. So when I brought the 3 down, 2/3 times 3, 3's cross out, just leaving you 2. Negative 8 plus 2 is negative 6. Now I take negative 6 times 2/3. I just multiplied straight across. That's negative 12/3, so that's negative 4. Add the column, that's negative 12. Negative 12 times 2/3, multiply your fraction straight across, you get negative 24/3, which is negative 8. So when you're dealing with a fraction in synthetic division, it's kind of hard to do all this arithmetic in your head, so you might want to do some of that on scratch paper. So the result that we got here is this. Remember that result gives you the quadratic equation. So you have 3x squared minus 6x minus 12. And I went to the quadratic formula because this thing doesn't factor. And it's possible you could have done this a little bit differently than I did. But the idea is if you have a common factor, take it out. Because if you don't, you're going to make the work on the quadratic formula more difficult than you need to. So I took a 3 out, so that would leave x squared minus 2x minus 4. And then that way, when I solve this equation, well, a is now 1, b is negative 2, c is negative 4. All right, and that just makes the arithmetic easier. So after you get everything set up in the quadratic formula, you're going to end up getting to the place where you get 2 plus or minus square root of 20 over 2. Okay, I broke up the square root of 20 into square root of 4 times 5. Square root of 4 is 2. And then once I did that, notice I split it up. I do 2 over 2, and then 2 root 5 over 2 to get the other two zeros. Okay, so that's how that would work. And as far as the graph, let me just zoom out on this just a touch here. And you can look at the graph that I put over here. These are the zeros. This is the 2/3. That's the one that you're given. This is the 1 plus root 5. That's the 1 minus root 5, like that. Okay, so I'm going to go ahead and pause the video, and if you need to pause on that, do that and go over the problems. Then we're going to resume, and I'm going to move on to one extra topic on here. Okay, so I'm going to move on to the next topic, which is complex numbers. We haven't talked about complex numbers. College algebra, our discussion on this is going to be pretty limited to how it relates to complex zeros. So what a complex number is it's a number that can be written in the form a plus bi. There's two parts of it. There's a real part, a real number part, and I is an imaginary part. So I is defined to be the square root of -1. Okay, you know from your background that you're taught that you can't do a square root of a negative number, and you can't really because there's no real number solution. So if I was to do the square root of -1 on my calculator, it'll give me an error, okay, and it's going to say that there's not a real answer. But what there is there's an imaginary answer to it. So mathematicians sort of began to think about what would happen if the square root of -1 did exist. And that sounds oftentimes really kind of crazy to students, why a mathematician would think that. But complex numbers, they show up a lot in the natural world. They show up in quantum mechanics. There's a lot of places where they show up surprisingly. So, if we never imagined this existed, we wouldn't have made those kind of discoveries. And think about it this way. There was a time historically when people didn't know what a negative number was. I mean, they came across the arithmetic problem 2 minus 5, and they thought, well, that doesn't make any sense, but it does make sense. It makes perfectly good sense with money and things like that. So there have been historically times where we had to kind of invent negative numbers. We had to kind of invent fractions. Those things came up later. We had to imagine that such a thing existed. So the complex number idea came several hundred years ago. I can't exactly remember where that comes into play, maybe the 1500s in there, before we began to really develop the ideas of complex numbers. So the question I'm asking is, why does the square root of a negative number not give a real solution? Well, the idea is a square root. When we're doing a square root, we're always looking for the same number we multiply out together that would give this result. So we know if we had the square root of 4, there's no problem with that. It's just 2 times itself is positive 4, so there's no problem. But when there's a negative number, it's impossible. I mean, if you do -2 times -2, well, that would give you positive 4. So it can't be that. The only other possibility is 2 times 2, and that would give positive 4. So it's impossible to take the same number and multiply and get a negative number. Never works. Okay, so what I'm going to kind of train you through here is just how we work with imaginary numbers. So if you've got like the square root of -16, technically what you do is you change this to the square root of -1 times the square root of positive 16. Okay, but the square root of -1 is I, and the square root of 16 is 4. So the answer to that problem is written as 4i. And you can do that in your head, but technically that's how everything works out. The next problem is the same thing. You're going to break this up and write this as square root of -1 times square root of 225. Again, the square root of -1 is I. Square root of 225, if you don't know that, you could take your calculator and you would get 15. So the result of that is written as 15i. Okay. And then the rest of these examples just have a little bit of algebraic simplifications to them. If you run across a problem like this part C, you would do it the same way. You would write that as square root of -1 times square root of positive 5. That's I. And then you just write that as I root 5. And it's a good idea to put the I in front of the radical instead of writing it like this, Because a lot of times if students write it that way, they'll put the I under the radical, and that's not the case. I is separate from that square root of 5. Okay, all right, these will work the same way. Part D, you would start by writing this as square root of negative 1 times positive 8. So that would be I times the square root of 8. But you can break the square root of 8 into square root of 4 times 2. So what you would get then is square root of 4 is 2. So you'd write that as 2I times the square root of 2. Okay, so that's how that gets put together. And then the last problem is the same idea. You would write this as square root of negative 1 times square root of 48. So that's I times the square root of 48. Then you got to kind of work with this. 16 is a factor of 48. So you could write that like that. Okay, so square root of 16 is 4. So you write this as 4I times the square root of 3. So you're combining things we have learned how to do. We've simplified radicals. We're just combining this idea of a square root of a negative number. Okay, so since we haven't really covered complex numbers, you need to at least get solid with what I'm showing you here. So go ahead and pause the video, if you will, and work out these problems. Just make sure you're competent with these things, and then resume the answers, resume the video, check your answers, and then we'll do one last thing to finish up the section. Okay, so you can go ahead and check your answers, and really you can learn to do some of these in your head. Like the first row you can do in your head. You know that you have I because it's an imaginary number, and the square root of 9 is 3. Same thing with the next problem. The square root of 100 is 10, because 10 times 10 is 100. So you can just write that as 10I. And number 3 is 4I. So as I'm teaching this, I'm breaking this up, showing you technically how you reason through this. So you're just saying square root of negative 1 times square root of positive 9. So that's I times 3, or 3I. But the first row, 1, 2, and 3, you can process in your head and get that down pretty easily. 4 and 5 are just checking to see, are you getting skillful with simplifying radicals? So basically the 50 gets broken up into 25 times 2. The reason we do that is because the square root of 25 is 5, and then the 5I needs to be in front of that radical. You want to write that exactly that way. Okay, the next one, 27 can be broken up into 9 times 3. The square root of 9 is 3, so you get 3I times square root of 3. So the reason we're going over this is when you're working with the quadratic formula, there's going to be times when you're going to have to work with square roots of negative numbers. So that's what we're looking at. Okay, so one last thing. Down at the bottom, I'm not going to go over how to add and subtract complex numbers. I guess I'll go ahead and just show you, but we're not going to deal with this any. Really, when you add two complex numbers, it can be thought of as just combining like terms. That's really all it is. So this would be 3 plus 12 would be 15. Negative 4i plus 6i is 2i. So that would be the complex number solution. And again, you write the complex number form as a number plus a number times I, a plus bi. If you subtract two complex numbers, it's just like algebra that you've learned. This would be 9 plus 2i minus 10 plus 8i. We've learned how to subtract polynomials. So it's just a matter of changing the signs. And then when you put this together, 9 minus 10 is negative 1. 2i plus 8i is plus 10i. So complex numbers could be added, subtracted, multiplied, and divided. I'm not going to go through multiplication and division, though, at this point in time. So on the next page, we're going to do complex zeros, and you'll see that the ideas are pretty similar to what we did. So a complex number will have a form a plus bi. And one thing I want to mention about this, we have what's called the complex conjugates theorem. And what it says is if you know this is a zero, then this one will automatically be the zero. So if you knew that 3 plus 2i was a solution, then so is 3 minus 2i. So they come in pairs. Complex numbers are going to be in pairs when they are zeros of polynomials. The other thing we're going to notice is a complex solution is not going to be an x-intercept. Okay, what it's going to do is a complex number, if it's plugged into the polynomial, will make the polynomial zero. That's why it's still a zero, because it makes the polynomial zero. But it won't be an x-intercept because you have a different system that you graph complex numbers on. You don't graph them on an xy coordinate plane like we've been doing. Okay, so let's kind of see what we're getting into here. So this one, I'm giving you your first zero as -1. So we do have a third degree polynomial. That means the maximum number of zeros is 3. And that's all we've been really dealing with so far, is just third degree polynomials. So we're going to synthetically divide. I'm not giving you a factor this time. I'm just telling you that -1 is a 0. So put your coefficients, and then you want to go ahead and do your synthetic division. Since I'm telling you it's a 0, you know that you're going to get a remainder of 0. If you don't, you're messing up with your arithmetic. Okay, so let's see what happens on this. Bring the 1 down. -1 times 1 is -1. Add the column to get -6. -1 times -6 is 6. 7 plus 6 is 13. -1 times 13 is -13. So we get the remainder we expect to get. So what this is going to result in then is the power goes down. So this result would really be 1x squared minus 6x plus 13. So that is the resulting quadratic equation. So what we're going to do is take this quadratic equation, which does not factor. We're going to set that to 0, and we're going to have to use the quadratic formula to do that. So in this problem, a is going to be 1, b is going to be -6, and then c is going to be 13. Okay, so we're going to plug that into the quadratic formula. So we're going to have -b, b is -6, plus or minus the square root of b squared. So that would be -6 squared, minus 4 times a, which is 1, times c, which is 13, and then all over 2a, or 2 times 1, like that. Okay, so you want to make sure you get everything in the quadratic formula very carefully. Be aware with the -b part. Okay, a negative is going to make that a +6. So let's crunch this out and see what we get. We get +6 plus or minus the square root. You could do all this on a calculator if you wanted to. I mean, you can do some of it in your head too. But if you did this, I mean, you can carefully do this on a calculator if you want to. So -6 squared minus 4 times 1 times 13. That expression under the radical, we call that the discriminant. So that's going to give -16 over 2. So when that negative number pops up under that radical, that tells you we have a complex number. We have a complex number solution. So we learned a little while ago that if we deal with the square root of -16, you know, that's just I times the positive square root of 16. So that's 4i. So this would become 6 plus or minus 4i all over 2. And then what you want to do is just go through and spread it out, you know, tear apart the fraction in a sense. So 6 over 2 plus or minus 4i over 2 is going to give you 6 divided by 2 is 3, and then 4 divided by 2 is 2, so you're going to get this. So your zeros are going to be this. I gave you that -1 was your first zero. Now these things come in pairs, and the reason they come in pairs is because of the plus or minus that exists from the quadratic formula. So we'll have 3 minus 2i would be one of your zeros, and so would 3 plus 2i, like that. Okay, so it's the same principle. Only thing that's different is occasionally you're going to come up with some complex number solutions, zeros of polynomials. All right, now let me show you what happens on the graph on this. So put this function in your graphing calculator. There's kind of a key difference on this. So we're going to graph x to the third, and then minus 5x to the second, plus 7x, plus 13. I'll graph that. Okay, and I'm using this window that I used on previous examples. Now, what I want to show you on this is, although we have 3 zeros, we only have one x-intercept, and that one x-intercept is the real number -1. So since you got 2 complex number solutions, those will not be x-intercepts. Okay, that's really what I'm wanting you to get from looking at the graph on this then. Okay, so you're only going to get one intercept, so you want to go through and just make a note of that. So you have x equals -1. So there's just one x-intercept. Okay, but it has all of the endpoint behavior we would expect for a polynomial. It only crosses one time. Okay, so there's no crossing or touching of complex numbers. All right, so synthetic division is the big deal in this, and then solving the resulting quadratic equation. It's kind of repetitive. It'll be the same thing over and over again with little slight twists and turns to the problem. Okay, so let's see. I'm going to do 2 more on the next page. Now, these we're going to take a different approach on. We're not going to do synthetic division. We're going to factor these. So I think on your web work homework, you'll see some things where if you can factor a third-degree polynomial, then you want to try to do that. So what you encounter here is these problems have 4 terms, and if you have 4 terms, then it's possible that you could do what we call factor by grouping. All right, and factor by grouping kind of works like this. What you're going to do is you're going to group together the first 2 terms. So you're going to put a set of parentheses around that first pair like that. That plus sign is going to go right there. Everything's just coming down. Then we're going to put the 4x minus 12 in a set of parentheses like that. So we're grouping them together. Typically, most of the time what works is you group the first 2 and the last pair. Okay, now what you do is you take out common factors. So if you look at this, you have an x squared and an x to the third. Don't look at the 4x minus 12. We can take x squared out of this. Okay, then you can do this in your head. X squared has to be multiplied by x in order to get x to the third, and x squared has to be multiplied by 3 in order to get 3x squared. Okay, next part right here, 4 divides into 4 and 4 goes into 12, so you can take a 4 out of that, and notice 4 times x is 4x, and 4 times 3 is going to be 12. So you got to be skilled at taking out your common factor. So what's going to happen on factor by grouping is typically what's left in the parentheses turns out to be the same thing. So that's another common factor. So you're going to take the x minus 3 out as a common factor. Okay, now usually the way I teach this in class is I take my hands and I cover up the x minus 3 part. And when you see that, you're going to see what's left over is the x plus 4 part. X squared plus 4 goes there. So that's how you do factor by grouping. Okay, one thing I want to show you just at the side, and you don't have to write this down, but when you factor, you can check your factor. So if I go through and FOIL this, look what happens. I got x times x squared is x to the third. The outside term is plus 4x. Inside term's negative 3x squared. And then negative 3 times 4 is negative 12. If you compare that to the original problem, it's the same. These are in a different order, but all the terms are the same. So you have the power and the ability to tell you factored something right by multiplying it out. Okay, so here's the next thing we do. We go ahead and set each factor equal to 0, and we're going to solve each equation separately. Okay, this one you can solve in your head. You could add 3 to both sides. So that means your first 0 is x equals 3. Okay, so we know that is a definite solution of that equation. The next one, we're going to do this. We're going to subtract 4 from both sides. We will have x squared equals negative 4. Now we will take the square root of both sides, and this is a complex number. So you're going to get x. When you do a square root of both sides, make sure you have the plus and minus, and then this would be 2i. It's an imaginary number. We know the square root of 4 is 2i. Square root of negative 4 is 2i. Okay, so basically your answers to this problem are going to be 3, negative 2i, and positive 2i like this. Now the complex conjugates theorem told you that your complex numbers always come in pairs. So you have negative 2i, you have positive 2i. All right, so that's how that works out. Okay, so we're going to just kind of focus on factoring on this. The next problem, we're going to pretty well do this the same way. So put parentheses around the first pair. Also, bring that middle plus sign down. It's important that middle plus sign is in the middle of 2 parentheses. And then group together 8x plus 24 like that. Then we'll take out common factors. It's very similar to the last problem. You have an x squared as your common factor that comes out of here. So that'll leave you x plus 3 when you take that out. You can take an 8 out of this, so that will be 8 times x plus 3, like that. Okay, just kind of in your head, multiply it out. See, x squared times x is x to the third. X squared times 3 is 3x squared. You make a move in factoring, you check your answer. 8 times x is 8x, 8 times 3 is 24. Now what happens, just like the last problem, is this is another common factor. That x plus 3, the whole entire thing, is a common factor. So it pulls out of this, and then you can just kind of take your hands and cover up the x plus 3. You're going to see what's left is going to be the x squared plus 8. So we have that factored. If you foiled x plus 3 times x squared plus 8, it would take you back to the original problem. So now what we're going to do is we take each factor, x plus 3 equals 0. We solve that equation. Then we take x squared plus 8 equals 0, and we solve that equation. Okay, so the first 0 is going to give you x equals negative 3. That's one solution to the equation. Over here, you're going to subtract 8 from both sides. That'll give you x squared equals negative 8. Square root both sides, and see you're going to have an imaginary number now. So you want to have that plus or minus, and then you're going to, this will go like this, okay? You know you have an I, and then the square root of 8 can be broken up into 4 times 2. So what you'll get is square root of 4 is 2, so you get 2i times the square root of 2. So that would be your 3 solutions of that equation then. I'm just going to write it as negative 3, negative 2i root 2, and positive 2i root 2. So those are the answers to that problem. Okay, so that's how that goes. Now, one thing I want to show you on this too is these equations are checkable the same way that we've been checking our graphs and zeros. So if I graph part C, if I just graph that polynomial and put that in, I'll show you what happens. You're going to get x to the third and plus 3x to the second. Not that. I don't know what I'm doing there. Okay, x to the third. Then you got to come down out of that exponent, and then it would be plus 3x to the second, and plus 8x, and finally plus 24. So if we put this in, the polynomial is going to only have one x-intercept. That x-intercept's negative 3. So one of our zeros was negative 3. So if you trace it negative 3, that's going to give you that x-intercept. The 2 other complex number solutions are not x-intercepts. Okay? All right. So I'll let you do the next 3 problems. This is a good place to pause the video if you need to process what I was going through. You need to write notes down and look over things. That's a good time to pause. Okay. Then when you're ready to try your problems, go ahead and move on, okay? All right, so pause, and when you resume, you should see the answers magically displayed. Okay, so you can go ahead and check the answers. Here's what you should have got on 1 and 2. Answer to number 1 is 4, -5, and 5i. The key is that you did the factor by grouping correctly. So your two factors are x minus 4, x squared plus 25. Then when you solve these two equations, you get a 4, and you get a plus or minus 5i, right? Number 2 works out the same way. The answers are -12, -3i, and 3i. So the factoring by grouping works the same way. Your factors are x plus 12, x squared plus 9. Solve the equations, you'll get -12, and then the two complex solutions are 3 and -3i. Now, number 3, I did an example like that a little earlier before I did the factoring. So this time I'm giving you a 0 as 1. So if you weren't sure what to do on this problem, the idea is this will not factor. If you tried to factor that by grouping, you wouldn't have any success doing it. But you don't need to because I gave you a 0 anyway. So if you synthetically divide this polynomial by 1, you'll have the remainder of 0. So you end up with the quadratic equation, x squared minus 8x plus 17 equals 0. And what I did from here is I went to the quadratic formula. A is going to be 1, b is -8, c is 17. And then when I go through the details of this and get the arithmetic, I get down to this point. Square root of -4 is 2i. So now I've got 8 over 2 plus or minus 2i over 2. So I get 4 plus or minus the square root of I. So if you have a given 0, you can synthetically divide that so that you'll end up with a quadratic equation that you can solve. Okay, so that will be the end of the section. There's lots of synthetic division. It's just really kind of one central idea of using synthetic division to find zeros, whether they be real zeros or complex zeros. All right, hope you enjoyed the video and as much as you possibly can, and I'll see you in class soon.